Exercise number 6 asks us to find the length of the curve described by the parametric vector equation r of t equals cosine of t I plus sine of t j plus the natural log of the cosine of t k, where t runs from 0 to pi over 4. Now, there are several ways we could approach this. You could dive straight into one of the formulas in the textbook. I often like to kind of organize my thoughts and take things in smaller pieces. The general idea when trying to find the length of an arc or curve of any sort is that the length is usually going to be the integral along that curve. For right now, this is just an informal notation. The bounds will depend on what our variables are, of some differential arc length ds. If you go back to Calc 2 and you look at all the different arc length formulas you accumulated throughout the course of that class, you'll find that they all had this basic form where the ds was some radical of something, right? And it just sort of depends on your context. Now, in this class, you might use the form that, okay, well, ds will be the square root of, and if we think of these as x, y, and z as parametric functions of t, we could say that it is dx by dt squared plus dy by dt squared plus dz by dt squared. We have the square root of all of that times dt. This is one of the algebraic rearrangements that we can get from the Pythagorean theorem on the differential arc length ds. But this is still pretty large, and there's a lot of things here to pack into that. So actually, I will take a slightly different approach here. Still starting off the same, but now remembering that another expression for ds, when we're working parametrically in any number of dimensions, is that we can say that ds is the magnitude of the tangent vector dt. We have the length of r prime of t in here. And that suggests a further unpacking. Let's break this down into as small a problem as possible. And let's just find r prime of t first. Okay. So first component is cosine. The derivative of cosine is negative sine. The second component is sine. Its derivative is cosine. And for the third component, we have the natural log of cosine t. Derivative of natural log is 1 over that thing, so we have something over cosine t. Derivative of cosine is negative sine. We do this by the chain rule, of course. And we have this. We should clean this up a little bit, simplify, because we have more work to do, and we don't want to leave that last component the way it is. That is much too messy. That is the negative of the tangent of t. So that is r prime of t. We want the magnitude of r prime of t. So that'll be the square root of the first component squared. So we have sine squared t, plus the second component squared, cosine squared t, plus the third component squared, tangent squared t. Square root of all of that. Now we could drop this in, but keep in mind we're going to have that dt inside of an integral, right? And this does not look like something that's easy to integrate, so let's continue to simplify, keeping in mind we want to get down to the point where we can integrate the expression we end up with. Well, sine squared t plus cosine squared t equals 1. So we have 1 plus the tangent squared of t. And 1 plus tangent squared is secant squared. So that's nice. We have a square root of secant squared, and a square root of something squared is the absolute value of that thing. Now again, we want to take an integral. And absolute values inside of integrals usually need to be broken up. Let's see if we can simplify this any further. So we have the absolute value of secant t. If we come back and look at the bounds on t, t ranges from 0 to pi over 4. So we could say that is in the first quadrant, thinking in terms of angles. The secant of something there, secant is reciprocal of cosine. Well, all the trig functions, doesn't really matter. The trig functions are positive in that first quadrant. So specifically for this range of t values, that absolute value will be the secant of t, because it'll never be negative. So our arc length is an integral of ds. ds was the magnitude of r prime of t, which we found that in this particular case simplifies down to secant of t. We have the differential dt in there, right? ds equals the magnitude dt. And we need to integrate along whatever the curve is. We're told that t runs from 0 to pi over 4, so those are the bounds on the integral. And you see that at this point we have reduced this to what was a late Calc 1 or early Calc 2 problem. I forget where the antiderivative of secant was introduced, but we have the natural log of the absolute value of the secant of t plus the tangent of t. And we need to evaluate that from 0 to pi over 4. So plugging in and evaluating, we have natural log of absolute value, secant of pi over 4. Well, the cosine of pi over 4 is 1 over radical 2. So the secant of pi over 4 will be the reciprocal of that, which is just radical 2. The tangent of pi over 4 is 1. And we subtract natural log of absolute value of secant of 0. Cosine of 0 is 1. So the secant of 0 is also 1. Plus the tangent of 0 is 0. So we have that. 1 plus 0 is 1. Absolute value of 1 is 1. Natural log of 1 is 0. So that whole term is 0. And what we're left with, if we simplify a little bit, root 2 plus 1 is a positive number, so we no longer need to write the absolute values. And we have the natural log of the square root of 2 plus 1. Okay, well, you might look at that and sort of shrug and say, okay, is that right? How do we know? Do we have any idea? Who's to say? How can we tell? Well, let's take a look at the original curve. We're talking about an arc length, the length of a curve. This is a geometric object, right? So we might be able to, if we can get a rough sense of what this looks like, we might be able to get a rough estimate of kind of what numbers we should expect and check to see if that's reasonably accurate. So let's take, let's kind of try to produce a rough sketch of what this thing looks like. Just very crudely here. So we'll take an x, z, y, and let's think about where this starts. When t equals 0, the cosine of 0 is 1, sine of 0 is 0. Again, cosine of 0 is 1, but the natural log of 1 is 0, so we have 1, 0, 0. So this curve begins at 1 on the x-axis, coordinates 1, 0, 0. As t increases, let's ignore this third component for a moment. I'll come back to that in just a second. Looking at these first two, we have cosine t, sine t. Well, hopefully you recognize that's the x, y coordinates on a unit circle, right? So as t increases from 0 to pi over 4, you can think about the angle off of the x-axis increasing from 0 to pi over 4, and this would swing out toward that point, right? Now what's going to happen with this third component? So again, when t is 0, we have the cosine of 0 is 1, and the natural log of 1 is 0. As t increases, the cosine decreases, but at first it stays very close to 1. So at first, this is just slightly less than 1, which means its natural log is just slightly less than 0. It's negative, but only a tiny bit. So at first, this is basically following that arc in the xy plane. It's not quite in the xy plane, it's a little bit below it, but it's pretty much following that arc. And as t increases further and further, the cosine drops more, the natural log is going to drop more. So as this follows this arc around, it will gradually start to drop off noticeably until it gets to some point here, right? So looking directly down on this, if we were just looking the xy plane, this would look like it just follows the, eighth of a circle arc from here to here. But in actuality, in the depth, it kind of drops down below the plane a little bit. Now, if it were just that arc, we're going a distance of, we're going from 0 to pi over 4 on a circle of radius 1. That means that the arc length would be, if it was just that circle, it would be pi over 4, right? We computed instead an arc length of the natural log of the square root of 2 plus 1 for this curve that sort of bends a bit. It mostly follows that, but it's going to drop down, and that's going to add a little bit of length, isn't it? So we expect this value to be modestly larger than pi over 4. Noticeably larger, but not gigantic. It should be just a little bit larger than pi over 4. And these are difficult to estimate mentally, but if you put each of these into your calculator, you will find, in fact, that the computed value for our arc length is a little bit bigger than what would have been just the 1/8 arc of the unit circle. I believe I worked this out earlier, and I believe it came out to something like about a 12% increase, something like that. Again, noticeable, but modest. So any of these, geometric problems where you have some means by which you could sort of roughly estimate how long something is, then that can be very useful. Even if you don't get as precise as I did with the arc of a circle and all of that, even just looking at the thing and realizing, well, draw this picture, it shouldn't be more than about 1 or so, and if you work this out, I think it comes out to be like a 0.88 or somewhere around that vicinity. So that's about right. If you draw a picture like this, and then you compute your number that you got, and you find a very tiny number or a very large number, then you should be suspicious of your computations and go back through, try to find where your mistake was.